In this lecture, we begin our study of number theory, which, as its name suggests, is the study of numbers. Number theory has been called the queen of mathematics, suggesting that the subject is both beautiful and pure. Many mathematicians study number theory simply for its beautiful patterns and give no thought to applying it to anything real. One of the great number theorists of the last century was the English mathematician G.H. Hardy. Hardy said that he was interested in mathematics only as a creative art. He wrote one of the classic textbooks on number theory, An Introduction to the Theory of Numbers, co-authored with E.M. Wright. Yet, for all of Hardy's mathematical achievements, he claimed that he had never done anything useful. He said, "No discovery of mine has made, or is likely to make, directly or indirectly, for good or ill, the least difference to anyone in the world." And yet, despite the fact that his co-author was right, I think that Hardy was wrong. In these lectures on number theory, we will start by proving some important theorems about numbers and their properties, mostly pertaining to divisibility and prime factorization. But we'll also see how this basic information has many nice applications as well. From ISBN numbers on books, to card shuffling, to public key cryptography for safe and secure financial transactions. So here we go. Behold the positive numbers. 1, 2, 3, 4, all lined up in a row. If we append the number 0 to this list, we have the non-negative numbers. 0, 1, 2, 3, etc., sometimes called the whole numbers. If we include the negative numbers and attach that to our list, -1, -2, -3, and so on, when we put the non-negative numbers and the negative numbers together, we have what are called the integers. Right? You could say that they're centered at 0, and we have the positive numbers to the right and the negative numbers to the left. Now, one of the challenges of teaching number theory is that you already sort of know too much, right? You've been playing with numbers ever since you've been in school. And so there are things that you know about numbers that were never rigorously explained to you. So the question is, one of the challenges, where do you start? What are you allowed to assume? What are we going to be allowed to assume as we explore the theory of numbers? So I'm going to let you assume some of these facts, okay? I mean, you can do them without proving them or questioning them. That for any integers x, y, and z, that x plus y is always an integer, and x times y is always an integer. That is, when you add or multiply integers together, you get an integer back. You know how 0 works, and how 1 works, and how negative numbers work, right? X plus 0 is x. X times 1 is x. X plus negative x gives you 0. You're familiar with the commutative law of addition and multiplication. X plus y is y plus x. X times y is y times x. The associative law of addition and multiplication. That says that you can parenthesize things however you'd like, and that's not going to change your answer. In other words, x plus y plus z is the same as x plus y plus z, regardless of whether I put the parentheses around x plus y or the parentheses around y plus z. Similarly, x times y times z is the same as x times y times z. That's the associative law of multiplication. We even have a distributive law which combines the two, right? X times y plus z is x times y plus x times z. So you're allowed to know all these things, and you're even allowed to know about induction. Perhaps I should better spell out the things that you aren't supposed to know yet. All right, these are what we're going to address all these topics in due time, but for now, forget whatever you may have learned about greatest common divisors, prime numbers, or modular arithmetic. But by the end of this lecture, we'll certainly know a lot about the first topic, and by the end of the lecture after that, we'll know a lot about the second topic, primes. We know that when you add, subtract, or multiply integers, you get another integer, right? Those were some of the things we were allowed to assume. But not so with division. When you divide two integers, you usually don't get another integer. But there's something very important we can say about division. In fact, this is our first theorem of number theory, the division theorem. It says this: when we divide two positive integers, let's say we're dividing A by D, D as in divisor, we get a quotient and a remainder. More precisely, if A is bigger than 0 and D is bigger than 0, there are unique integers Q and R such that A is equal to D times Q plus R. And what can I say about my remainder? My remainder is always smaller than my divisor. My remainder, R, lives between 0 and D. It could equal 0 if the divisor goes into the number with no remainder, but otherwise we'll get a positive number strictly between 0 and D. So for example, if we took A is 29 and D is 7, then 29 divided by 7 will give us a quotient of 4 and a remainder of 1. Right? 29 is equal to 7 times 4 plus 1. Now we're going to be talking a lot about remainders, maybe more than you're accustomed to. So we have a notation for that. We say that the remainder in this situation is equal to 29 mod 7. So 29 mod 7 means the remainder that you get when you divide 29 by 7. In this case, that's equal to 1. Let's do another example just to be crystal clear. So 53 mod 10 is 3, because when we divide 53 by 10, we get a quotient of 5 and a remainder of 3. Let me emphasize again, the remainder that you get will always be smaller than your divisor. So 3 is less than 10. It's a subtle point, but an important one. Let's give a picture proof of the division theorem. Right? So if A and D are greater than 0, they're unique integers Q and R, such that A equals DQ plus R, and the remainder is between 0 and D. Here, if you envision the number line, you see we have the numbers 0, D, 2D, 3D, 4D. The number A, being positive, has to live somewhere on that line, and therefore it has to live between two consecutive multiples of D. It has to live between, say, Q times D plus some other number, Q plus 1 times D. That gives us our quotient Q. On the other hand, the remainder that we get is going to be the distance between A and QD. Right? And that distance can't be any larger than the distance between QD and Q plus 1D. That distance is D. So the remainder R has to be strictly less than D. If R is equal to 0, we say that D divides A. Okay, so here's the official definition. We say that D divides A if there exists an integer Q such that A is equal to D times Q. We talk about divisors so often that we have a special notation for that. We say that D divides A, and we use a vertical line to express the dividing operation. Okay? So another way of thinking of it, though it looks kind of backwards, is that D divides A if A over D, the fraction, the quantity A over D, is an integer. So for example, we can say 3 divides 12, 2 divides negative 6, right? Because 2 times negative 3 is negative 6. 7 divides 0 because 7 times 0 is 0, right? So 7 does divide 0. However, we can't say that 0 divides 7, right? 7 over 0 isn't a number. All right, so just as one more example, the number 12 has divisors plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Those are the divisors of 12. Okay, let's do a warm-up theorem. All right, and this is actually, it's an obvious statement. It's one that should feel at least intuitively obvious, that if C divides B and B divides A, then by all that is sensible, C should divide A. Now, it seems perfectly clear, but let's prove it. Let's rigorously prove it using what we know about dividing. So suppose C divides B and B divides A. Right? It's an if-then theorem. So we start by supposing the if. We want to say a bunch of logical things and eventually conclude the them. The then, not the them. Okay, so for instance, suppose C divides B and B divides A. Our goal is to conclude that C divides A. So since C divides B, that means that B can be written as C times an integer, Q1. And since B divides A is equal to B times another integer. Say that other integer was Q2. Therefore, A, which is equal to BQ2, but we can replace B with CQ1 to get the expression C times Q1, Q2. And since Q1, Q2 is an integer, right, it's the product of two integers, we've written A as C times an integer, which is what you need to do in order to say C divides A, because C times some integer gives us A. Next, I'd like to prove theorems of the following form. I'd like to say if D divides A and D divides B, then D divides A plus B, D divides A minus B, D divides A times B. The good news is we can prove all these theorems and much more in one fell swoop with the following useful theorem that's called the integer combination theorem, or as I like to call it, the IC theorem, because by the time you're done with it, you say, I see. Okay, so if D divides A and D divides B, then D divides any integer combination of A and B. What I mean by that is D divides any number of the form AX plus BY, where X and Y are integers. Everything's an integer in this lecture, unless I say otherwise. Okay, the proof of this is very, very similar to the last one. I'll go through it quickly. So suppose D divides A and D divides B. That means that A is equal to D times an integer Q1. B is equal to D times another integer Q2. Therefore, AX plus BY, I can replace A with DQ1 and B with DQ2, and I'll get the expression dq1x plus dq2y. By the distributive law, I can pull out the d to get d times q1x plus q2y. But we know that q1x plus q2y is an integer, so we have what we need to say that d divides ax plus by. So, as we mentioned before, 12 has divisors plus or minus 1, 2, 3, 4, 6, and 12. 30 has even more divisors. It's plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. We say that they have common divisors plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The greatest of those common divisors is called, naturally enough, the greatest common divisor. It's one of those names that really defines itself, right? So our notation for that is that is GCD of 12 and 30 is equal to 6. Now we use GCDs so often in mathematics that mathematicians sometimes get even more efficient and don't even write the word GCD next to it. So when we're doing a long chain of calculations, we just might write in parentheses 12, 30 to represent the GCD of 12, 30, which is the number 6. It's a little confusing at first, but you get used to it. So for instance, the GCD of 12 and 30 is 6. The GCD of 12 and negative 30 is also 6. The GCD of 16 and 9, does anything go into 16 and 9? Yeah, 1 does. And in fact, 1 will divide any two numbers, and sometimes that's the best you can do. So 16 and 9 have a GCD of 1. When two numbers have a GCD of 1, by the way, we say that they are relatively prime. That's a very important vocabulary word. We'll use that over and over. So 16 and 9 here are relatively prime. A few other GCDs. The GCD of 7 and 56 is 7, because 7 goes into both numbers. How about the GCD of 7 and 0? Yeah, that's also 7, because 7 divides 7 and 7 divides 0. Okay, here's a question now. What numbers can be created using 12 and 30 as your building blocks? Okay, so specifically, what numbers can be expressed in the form 12x plus 30y, where x and y can be any integers? All right, question, first of all, can every number be written in the form 12x plus 30y? No, because you see that 12 is even and 30 is even, and so 12x plus 30y must always be even. Could you create the number 4? No, because 12x plus 30y, we can factor out 6 and get that that's 6 times 2x plus 5y, and 2x plus 5y is always an integer, so 12x plus 30y always has to be a multiple of 6. All right, can we create the number 6? Yes, we can, and I'll just give it to you. There's many ways to do it, but the easiest way is 12 times 3 plus 30 times negative 1, we're allowed to use negative numbers, gives us 36 minus 30, that's equal to 6. Okay, can we create every multiple of 6 using 12 and 30 as our building blocks? Sure, we can take that last equation and multiply it by any number. So if you want to create the number 6m, then just multiply that equation by m, and you'll get 12 times 3m plus 30 times negative m gives us 6m. Okay, now suppose that we're using the numbers 16 and 9 as our building blocks. 16 and 9 are relatively prime. Can we create any number so that it's in the form 16x plus 9y? Can all numbers be created using these building blocks, 16 and 9? And the answer is yes. And to prove that to you, all I have to do is construct the number 1 using 16 and 9. And once I've created the number 1, I can create anything. So here we go. 16 times 4 plus 9 times negative 7 is 64 minus 63, which is 1. And now if I want to create any number, I just take that equation and multiply it by m. So 16 times 4m plus 9 times negative 7m gives me the arbitrary number m. We can only create the number 1 if our building blocks are relatively prime. The interesting question is, if a and b are relatively prime, can we always create the number 1, like we did with 16 and 9? If so, then we can create any number. The next theorem, which we're going to use several times in this course, dates back to the 18th century and says yes, if you have numbers that are relatively prime, then you can create the number 1 from them. Specifically, this is called Bézout's theorem, says that if a and b are relatively prime, then there have to exist integers x and y so that ax plus by equals 1. So here's the idea of the proof. It says, well, let ax by be anything. So give me any x, give me any y, and look at what ax plus by is. All right? And if ax plus by is bigger than 1, I can always find, to make ax plus by, I can always find some number bigger than 1, then we can find a new x and a new y to create a smaller positive integer. So if ax plus by is any old positive number and that's bigger than 1, then I'm going to show that I can create a smaller positive number. And I'm going to repeat that argument until I eventually find an x and a y that gives me the number 1. This kind of argument is known as reductio ad absurdum, and it was used by number theorists like Fermat beginning in the 17th century, before proofs by induction became more standard. Okay, so here's the proof of Bézout's theorem. Suppose ax plus by was equal to some positive number d, and let's assume that d was bigger than 1. If it was equal to 1, we'd be done. So let's assume that d was bigger than 1. Now, since a and b are relatively prime, this number d can't divide a and b, because otherwise A and B would have a common divisor, D, that was bigger than 1. So D can't divide both of them. Let's suppose it doesn't divide A, all right? So then by the division algorithm, if I divide the number D into A, I'm going to get a positive remainder. I'm not going to get a remainder of 0, right? Because D doesn't divide into A. All right, and the remainder, as always, is going to be less than my divisor D. Therefore, I can write A in the form dq plus r, where r lives strictly between 0 and D. Now, I'll rewrite that equation to say that r is equal to A minus dq. And then I'm going to write D in the form ax plus by, right? Because that's how we got started. So that says that r is equal to A minus the quantity ax plus by times q. Now I can rearrange that equation, right? Pull out an A, pull out of B to get A times 1 minus xq plus B times yq. But 1 minus xq is an integer, and yq is an integer. Therefore, I've written that remainder r as an integer combination of A and B. But r was a positive number that was smaller than D. Since I have a smaller number than D, I could do this process again with writing ax plus by as r this time. And just keep on doing that and doing that, repeating this argument, we'll eventually find an x and a y that gives us 1. Okay, what if A and B are not relatively prime? Bezout can handle that too. More generally, if A and B have a greatest common divisor of G, then there exist integers x and y so that ax plus by equals G. The proof of that actually it comes very quickly from the last proof. If A over G and B over G, they have to be relatively prime integers. Why is that? Well, they have to be integers because G divides A and G divides B. And why are they relatively prime? Well, if they weren't relatively prime, then I'd be able to divide A and B by a number that was even bigger than G. But G was supposed to be the greatest common divisor, so that isn't possible. Therefore, A over G and B over G are relatively prime. So by Bezout's theorem from before, we know that A over G times x plus B over G times y is equal to 1 for some integers x and y. Multiplying that equation by G gives us ax plus by equals G. Okay, so if greatest common divisors are so important, how do we actually find them? The method that we're going to use is called Euclid's theorem, and this theorem is more than 2,000 years old. In fact, 9 of the books of Euclid are on the subject of geometry. When we think of Euclid, we usually think of geometry, but 4 of those books, books 7 to 10, are devoted to number theory. Euclid's algorithm, which is one of the oldest algorithms ever discovered, appears as the second proposition of Book 7. Although Euclid didn't have mod notation back then, that was invented by Gauss. Heck, the Greeks didn't even have algebra back then. Everything was done geometrically. So, for example, the Greeks didn't do division like we do today. They would do repeated subtraction. Like if they had to divide 29 by 7, they'd say, okay, 29, we'll subtract 7. All right, we're still positive. We'll subtract 7. Okay, we'll still subtract 7. We'll still subtract 7 until they can't subtract any further. That's how they did division back then. And they did it using lengths of lines. Okay, so how do you find GCDs? Here's the important theorem. Euclid's theorem says, for any integers a, b, and x, the greatest common divisor of A and B is the greatest common divisor of B and A minus BX. Here's the proof. Really, it's a one-sentence proof. Anything that divides A and B, any divisor of A and B, is also a divisor of B and A minus BX. We get that from the IC theorem. And vice versa. Anything that divides B and A minus BX has to divide b, because I just said so, I said it divided b, and it has to divide a, because a can be written as a minus bx plus bx. Since they have the same common divisors, then they have the same greatest common divisor. Okay? So that's the proof of Euclid's theorem. When computing the greatest common divisor in practice, we try and make the number x as large as possible. So suppose, for instance, when we divide a by b, we get a quotient q and a remainder r. Let's let x be q, so x is as large as possible. Then that would say, Euclid's theorem would say that the greatest common divisor of a and b is the greatest common divisor of b and a minus bq. But a minus bq is r. So Euclid's theorem reduces to the greatest common divisor of a and b is the greatest common divisor of b and r. But remember, we have a special name for that remainder. The remainder, when we divide a by b, is called a mod b. So the Euclidean algorithm, as it's known, says that the greatest common divisor of a and b is the greatest common divisor of b and a mod b. Let's do an example. If I want to find the greatest common divisor of 53 and 10, then Euclid says that's the same as the greatest common divisor of 10 and 53 mod 10. 53 mod 10 is what? It's 3, because 10 goes into 53 5 times with a remainder of 3. So the GCD of 53 and 10 is the same as the GCD of 10 and 3. Now, how do I find the GCD of 10 and 3? Well, that's the same as the GCD of 3 and 10 mod 3. And 10 mod 3 is 1. And the GCD of 3 and 1, we could, if we wanted to, say, well, obviously it's 1. But Euclid could say, well, it's the GCD of 1 and 3 mod 1. And there's no, 1 divides into everything, so 3 mod 1 is 0. And the GCD of 1 and 0 is 1. If we were to write this out in one neat little line, it would say 5310 goes to 10 and 3, goes to 3 and 1, goes to 1 and 0. And when we hit 0, the bells and whistles go off, and we can say the answer is 1. Here's an even larger problem. If I said, what's the greatest common divisor of 4593 and 453? Off the top of your head, hard to see, right? But Euclid's algorithm says, well, I see that 453 goes into 4593 10 times with a remainder of 63. So that's going to be the same as the GCD of 453 and 63. And then I'll divide 63 into 453. That goes in 7 times with a remainder of 12. So we get the GCD of 63 and 12. And 12 goes into 63 5 times with a remainder of 3. So we get the GCD of 12 and 3. And the GCD of 12 and 3, well, 3 goes into 12 exactly, so we can stop here. The GCD of 3 and 0 is 3. Now, Euclid's algorithm is smart. That is, it not only finds the GCD, it also does what Bézout's theorem asked for you. It also will find the integer combination x and y that gives you the GCD. So these are, remember, the building blocks, 4593 and 453. What numbers could you create? Bézout's theorem says you can create its GCD, 3, and all multiples of 3. How would you find x and y? Euclid actually comes to the rescue. If you work through the chain of calculations that we had a moment ago, you'll see that the last statement involving 3 said that 3 is 63 minus 12 times 5. Now I can, using the equation above it, replace 12 with 453 minus 63 times 7 and rewrite that so we have an integer combination of 63 and 453. But I can replace 63 in terms of 4593 and 453 in terms of the original two numbers. Okay, and straightening that out, we get the integer combination that gives us the GCD, namely 3. You may wonder why we would want to find such an integer combination. Those will be important to us when we explore modular arithmetic and public key cryptography later on. The Euclidean algorithm was the first algorithm to be analyzed for its speed. In 1850, Lamé showed that the Euclidean algorithm is fast. He proved that if A is bigger than B, then the algorithm will find the greatest common divisor in under 5 log B steps. Now, log B is approximately, and is always slightly less than, the number of digits in B. So if, for instance, A and B are 100-digit numbers, then Euclid finds their greatest common divisor in under 500 steps, which is a piece of cake for a computer. Now, if you wanted to slow Euclid down, what are the worst numbers to give it? You try it. Give it 2 numbers below 100 and see how slow you can make it go. Like you might try 99 and 98, as big as you can. Well, Euclid solves that in 1 step. It gets it. It's no problem there. What if you tried 99 and 50? Nah, Euclid will take 2 steps to do that. The best numbers to give it are 89 and 55. Actually, they're the worst numbers to give it, the numbers that'll slow it down the most. And let's see, by Euclid's algorithm, that reduces to GCD of 55 and 34, then 34 and 21, then 21 and 13, then 13 and 8. Uh-oh, do you see what's happening? 8, 5, 5, 3, 3, 2, 2, 1. There are the Fibonacci numbers causing trouble again. Hey, speaking of Fibonacci numbers, we've just seen by this example that consecutive Fibonacci numbers will always be relatively prime. Here's another cool fact about them. If I asked you what's the greatest common divisor of 90 and 20, what would you tell me? 10, okay? Amazingly, the greatest common divisor of the 90th Fibonacci number and the 20th Fibonacci number, it's always a Fibonacci number, and it's the most poetic Fibonacci number you could ask for. It's the 10th Fibonacci number. And in general, the greatest common divisor of FA and FB is the greatest common divisor of A and B Fibonacci number. Truly an amazing theorem, one of my favorites. So far, we've seen that relatively prime numbers form additive building blocks for the integers. That is, starting with 2 relatively prime numbers, A and B, we can create any number by repeatedly adding and subtracting A and B. In what follows, we see how every number can be created multiplicatively using prime numbers. We'll do this in our next lecture as we explore the structure of numbers.